Hello.
Good afternoon, sir.
Yes, sir.
Good afternoon. So, yeah. Yeah, so before I start today's class, I hope you guys are enjoying your this winter. I cannot call it a break, but whatever, winter festivals and all those things. And any questions, any doubts of whatever has been done so far? Okay, so today how we are going to do is that today we will be having a more of a discussion kind of stuff rather than any. I mean, while we will be, finally we will be ending up doing something nice, but I want you guys to think of an algorithm that does this simple thing. Okay, I am giving you two polynomials, P1 and P2. Let's say P and Q, say. Okay, two polynomials of and I've guaranteed you that these polynomials are of degree at most n. It's a univariate polynomials of degree n. I want you guys to tell me what is the polynomial p times q. P times q. So you have to just multiply two polynomials. How will you do it? As you can expect, that this is a very important question that happens in any computational math, computational number theory. Even it's a very important thing in engineering also. So when you try to, the basic idea is to kind of multiply two polynomials. The question is that how will you multiply two polynomials? So why don't you guys think about it? So the n is that two polynomials which have degree two two single variate polynomials of degree n, at most n, and you have to multiply it. So give me an algorithm to solve it. Okay, you can take your time. But is the problem clear?
Sir, how is the input given?
Think about it. It's a very good question that you have asked.
Array of size and like each point. Is it an array of size and like okay, polynomial can be identified by
Ritobrato, I cannot hear your question. I mean, I think your voice is breaking for some reason. Hello?
Yes, sir. I was asking identified by its coefficient, and we know that it is of degree at most n. So is the input array of size n or something like that?
Okay, so good. So you have asked a very important question. I mean, I was going to, talk about it or next day. So question is that how is the input given? When I say that what's the polynomial, what do you mean by a polynomial? Now, okay, so one option is that you have been given as an array of n, array of n, say real numbers or complex numbers, whatever it is.
So won't it be n plus 1?
Okay, n plus 1 complex numbers. Okay, array of n plus 1 complex numbers or real numbers, doesn't matter. In some field you have been given.
Hello.
Yeah.
So we have two arrays, one of size n plus 1 and one of size n plus 1.
Right.
So we take the first element of one array, multiply it with all the elements of the other array, and then remove the.
Okay, very good. I mean, can you just tell me how much, what will be the time complexity of it, and can you just write a pseudocode for that?
Mn probably.
Mn, what is m?
The degrees of the two polynomials.
Okay, let's for the heck of it just assume that both of them are of degree at most n. Okay, so the arrays are of length n.
So n square.
N square. So can you just write a pseudocode for that? Okay, in your paper, just write a pseudocode for that, and also think a little bit. Okay, is this the best you can do? Okay. So good. So you guys are making very quick progress. So you have given me, you have asked me a very important question: how is the polynomial given? And one of you have given me an algorithm for multiplying those two. And you are saying that the algorithm is n square.
Sir,
Yeah.
sir, if the polynomials were given with respect to their roots,
Okay, with respect to their roots. Okay, say I give you the n roots. Then
just put them together. Because the roots are numbers that you can pass into the polynomial and get a 0. So any root of one polynomial will be a root of the
right.
product.
Just add them together. What do you mean by add them together?
Not add them together, just concatenate them. Like the list of roots, we can just merge the two sets. I mean, we just take the union of both the set of roots.
Okay. And
So,
that you want to keep it as a polynomial. Okay, fine. That is
right.
okay, good. That is a one way of doing it. If you the polynomials are given as just the roots of the polynomial, right? Then you
Yes.
kind of take the union and say that okay, these are the set of roots. Okay, but okay, good. So that is one good, very good point. So if you have been given it as a roots, then you can do it. But if you are given as a coefficient, then can you convert it to a representation of root easily, or the vice versa? So I mean, if so, in some sense, if I am right, let me write something over here. Okay, so you have been given two polynomials, P and Q. Right now, one option was that the input are the coefficients. Then you told that the multiplication takes order n square, right? So of degree less than or equal to n. So that's it for multiplication, right? So that is one thing that you told. The second thing was that told that if the inputs are as roots of the polynomials, then you can just I mean then it just order one time. Basically, you have just to just add them up, right? Or maybe order n just to kind of be.
Yes, sir. I mean, this is constant, right?
Yeah, to obtain roots of p times q. Okay, I agree completely. But problem is that there are two representations that we have come up with. Okay, the inputs are as a coefficient and inputs are as a root. Now, if somebody gives you the input as a coefficient, then if you can convert it quickly to a input or as roots, then you will make some good progress quickly. Then you can do it quickly.
So, but that would be equivalent to solving the polynomial, which is
yeah. What is the you have to think of what is the way of doing it. Yeah. Any other way? You can
So
think.
we can try a black box thing, like a recursive type. Like I mean, what I'm saying is, let's say I know how to multiply like up to linear polynomials, and
Up to linear
let's
number
say
what?
linear polynomials, like degree one
Okay,
polynomials.
fine.
Let's say if we take a quadratic polynomial, so that x square term, like the x square and x term, we can take out the x and convert it into one linear part and a constant part. So we can use the like the same subroutines per linear thing to compute the quadratic, but I don't think so. It's like going to be very efficient.
So you are trying to do a recursive thing
Yes, sir.
by trying to use a linear thing to solve a quadratic thing. Can you just, I mean, yeah, I don't see how to do that actually. I mean, how can you use a linear, multiplication of linear polynomials or degree d-1 polynomial as black box to obtain a multiplication for degree d polynomial?
Sir, up to d-1 as well.
Up to d-1 polynomials. Yeah, how will you do that? Okay, you can do that. Okay, you can write it out. Okay, you can do it.
Yes, sir. We can just just take the x out and then.
Right, you can do that. I agree. Okay, so any a of x can be written as b1 of x plus x times b2 of x, where degree of b1 of x, b1 and the degree of b2 is strictly less than degree of a.
Yes, sir.
And then you can use multiplication. Okay, good. So this is another way of doing it, but can you just compute, see how much time will it take to solve it like that? So this is another way of doing it. Good.
Sir, I think this also takes n squared.
This will also take
Yes,
n
sir. It will.
square.
Yes, sir. It will take n square, sir.
Yeah, why?
Sir, we can if we have like a tn minus 1, so we have so let's say that ax is of degree, like let's say this is a tn instance.
Yeah, so Tn this is n minus 1.
Yes, sir.
Nice. So T of n equals to, I think you might have to, so this is a and this, then there's another polynomial, right?
Yes, sir. Yes, sir.
So that can have 4 or something like that, I think, right? 4Tn minus 1 plus n, the order n.
Plus order n.
Right.
Combining, recombining. Yes, sir.
Okay. So this is one thing, but is this okay? So this is another thing that is getting n square also, right? Okay, this is a good observation actually.
Sir,
Yeah.
so we can also treat a polynomial as like a list of its values at n distinct points.
Excellent, you can do that. So it is kind of like this only in some sense. Here you are taking this n distinct point as n roots, right? But
So
you're
that
saying
the locations are not fixed. So we are
location are not
flexible
necessarily
to-
fixed, right? So a polynomial as evaluations at n distinct points. So if the points are, say, so if the points are, so if I have a polynomial p, okay, let's write it out as say a0 plus a1x plus a2x squared plus an x to the power n, right? I can also write it, and I have some values, I have some points, say y1 to yn are some points in the complex thing or the real thing, it doesn't matter.
So we need up to ym plus n, right?
For this one polynomial,
For this one polynomial n, but if we are multiplying degree,
do we
n,
need?
degree n, we need m plus n values.
Okay, we need m plus n values, right? Okay, good. So if we want to do it, then we need an n plus n value. Excellent.
Sir, this y1 to up to yn are what?
Okay, so some values, and then this polynomial can be represented as okay, P of y1 to P of yn. So this is an also equivalent. I mean, if I just, instead of giving you P of x, I mean, say P of x as the coefficients, instead of that, if I give you the evaluation of the polynomials at n places, then also I can specify a unique polynomial.
Yes, sir.
Yes, sir. And with respect to this note, this representation, the multiplication of two polynomials is very trivial. We just do pointwise multiplication.
You can do a pointwise multiplication. But okay, so okay, good. So if this is one representation that has been given to you, then there's another polynomial that has been given to you like this. Right? And you are trying to evaluate it at the same point. Y1 to yn, again, this is some value. So by the way, here I'm kind of say that I am going to give you, so here the representation can be given as a array of a0 to an minus 1, right? An plus 1, sorry, an. And here it is, you can also give it as this. Right, I'm making a mistake somewhere. This is a mistake I'm doing.
Sir, I think we will need n plus 1 points to
I think,
determine an
yes, I also think that we need n plus 1.
So how are you going to multiply using this notation?
How are you going to multiply? Yes, that's a very good point. But multiplication is easy. Okay, let's see. I mean, multiplication
How is
of what?
How is it different than the original, like n square?
Okay, just one second. Let me quickly just first show you, and then we will have a discussion on that. Okay, so this is the notice. So you have been given, say, if this was the input that in which it was given, and if this was the input in which it was given, then how do we have got p times q? What would we have got for p times q?
Py naught qy naught.
Yeah, so I could have easily, by multiplying it pointwise, I could get p dot q dot y naught
Yes, sir.
until p dot q dot yn, right? Or y, yeah.
But sir, given these, how will we what is the time complexity of retrieving the polynomial?
That's very good point. I mean, that's exactly, I think your friend was also asking. That, I mean, kind of, if I assume that this is the given, then I can produce p times q, this quantity, in order n time, right?
Yes, sir.
Okay, now I have also kind of brushed aside one important thing. Okay, this is something very important here. See, this one, okay, so assuming, now this is something, assuming that p times q is also a n degree polynomial, right? This is kind of very important. So you have been given p and q, they are also less than or equal to n degree polynomial. Then by specifying, if I can have and p and q are given as evaluations, okay, as n evaluation, then p times q can be obtained easily, obtained in order n times, right?
Yes, sir.
Good. So if p and q are there, it means p and q are given as these polynomials like this, then we are done. But of course, comes back to the same question that was there earlier. How can we move between this notation, can use a different, this notation, which is a notation of the coefficients or representation of the coefficients to this representation easily.
Sir, our goal is to find out the coefficients of the resultant, I mean, of the
The polynomial. Yes, yes.
Yeah.
Yes.
So, sir, from here, how can we get those coefficients? I did not get that.
I have not yet told you that. Okay. So tell me one thing quickly. Can you get it from here? If I give you this quantity, can you get the coefficient of the resulting coefficient?
So we have to solve a set of linear equations.
You have to solve certain linear equations. So let's see. If I give you this quantity, so forget P and Q. If I have a polynomial P, so what we are now talking about is this very special thing, right? You have been given a polynomial and it has these two representations. One is that a0 till an. Okay, so that means this polynomial P is basically summation of ai x to the power I equals to 0 to n, right? And I have the other representation, which is P of y0 to P of yn. But y0 and yn are known to us. Okay, so these are not unknown to us. P of y0 to P of, y0 to yn are known to us, and I've got P0 to Pyn. How can we move between these two? So given one, how do I produce the other? And how, given this one, how do I produce the other? So this is our question, right? Hello.
Sir,
Yes, sir.
hello.
Yeah.
So, will you kindly briefly tell the second representation, the expansion of the second representation?
Okay, so I have, so you fix some set of values y0 to yn in the field in which we are working. Okay, they're all distinct points. And the second representation is evaluation of the polynomial at those fixed points. So if I have a polynomial of degree n and I give you evaluation of the polynomial at n plus 1 distinct points, I am uniquely telling you what the polynomial is. Right?
Yes, interpolation.
Yes, it's simple interpolation, right? Now, question is that how do we quickly move from these two representations, between these two representations? What do we think here? How do I, if I have given this representation, okay, how do I move, get this a0 to an? Can you tell me?
We can use interpolation, right?
You can use interpolation, right?
Yeah.
Okay. But how much time does interpolation take?
N squared.
Interpolation will take n square. Right? Okay. Let's see some other way of doing it. Okay. What is this a0 to n? What is y0? y0 is nothing but, right? Of course, I'm not writing it very trivially. This is, so not, I'm saying not in y0. What is P of y0? P of y0 is nothing but a0 plus a1 times y0 plus an times y0 to the power n, right? What is P of y1? It's the same thing. a1 times y1 plus an times y1 to the power n. What is P of yn? Same thing. Yn to the power n. So which means that if I write y0 to yn as a column vector, I can write a matrix, namely which will have what? Okay, I want to write it as a dot product. Dot product will be, sorry.
Left hand side will be, sir, py0, py1.
Yes, so
Left.
this, This will be say A0 till AN. And this is 1, Y0, Y0 square till Y0N. 1, Y1, Y1 square, Y1 to the power N. 1, Yn, Yn square, Yn to the power N.
Won't that be Py0?
What?
Sir, LHS. So
Oh,
Py0.
yeah. It will be Py. Sorry. Yeah. Right. So in some sense, I can think of this as the Y vector is nothing but a big matrix A times a big A is not a very good idea. Say I will say that this Py vector, P vector is nothing but a big Y vector dot a column vector, right?
Yes, sir.
So if this vector, this matrix has some special structure, particularly if this matrix Y is invertible, then what can we say? We don't have to go through the interpolation or any such things. In that case, I can, if you are giving me this chunk, I can easily produce this chunk. Right?
So, but so if we want to find out the PYIs using the AIs,
Right.
we
I
just still
think-
have to do this multiplication
And-
matrix. Sorry.
Yes, we have to still do the multiplication matrix.
Okay, right. But then
Right.
you're saying that the reverse process is just as easy if we have the inverse matrix of this matrix
Yes,
beforehand.
but if the matrix, inverse matrix has a nice structure to it, then possibly multiplying, if the Y inverse is something particular structure, then possibly multiplying this two is not going to take n squared steps.
Oh, okay, because we have freedom over choosing the YIs.
That is where the main trick is.
Okay.
What are the YIs?
How should we choose the YIs so that we can make an optimized multiplication?
Yes, and more importantly, I have not even told you how I can, how do you even, okay, so given A0 to AN, how do you produce P of Y0 to P of YN? The standard multiplication is by multiplying these two things, right?
Right. The evaluation of this product is what.
The evaluation of this product,
Right.
which is order n square, right?
Right. That is also order n squared. Right.
So moving from coefficient representation to say the evaluation in representation, takes order n square in worst case. Now, why I am saying worst case? Because see, this is the most trivial way of doing it. Okay. But if the YIs have some nice structure, then can we do something?
So what if the YIs were the ith, ith and its root of unity or something like that?
Wonderful. How are you? What was the idea that you through which you managed to guess it?
So the structure, sir.
The structure. If yi is the nth root of unity, so which is right?
Yes, sir. Right.
Then
So maybe it's 2 pi.
2 pi, yeah. Okay. So if it is basically the nth root of unity, Okay, so which basically is also represented as Wn. Then what is this structure?
So this is Wn to the power I, right?
Yeah, I mean, yeah.
Sir, shouldn't it be n plus 1th root of unity?
Yes, it will be the n plus 1 root. You're right. I need the n plus 1th root. Right? In that case, what is this matrix? Let's see, how many of you can guess this matrix?
Is it like the rotation matrix, like something like that?
No, it's not. It's a matrix that you have seen. I'm 100% sure.
Yes, sir. I think it's sir.
So it's some sort of a cyclical form, right? It's
Yes.
so is there a name that we know?
Yes,
for
very
this?
famous name. You must have seen it.
So it's like all the diagonal entries and the super diagonal entries are equal. Jordan form or something.
No. It's not a form. It's a matrix. It's very matrix of the name.
Okay. So is it some sort of a nth root of a matrix? Like, I'm not sure.
You've seen this matrix, no?
Oh yes, sir. So, but this
Yes,
is a
sir.
name that we give for a general matrix of this form, right?
I mean, it's a general matrix of this form, but particularly with the CIs, you can, that's exactly how the first Waldenbord matrix was defined.
Oh, okay. Because so we've learned it in this context of any matrix of this form in the general form.
Okay.
That we've seen here. That is a VDM matrix.
Okay.
Did we learn it like what determinant type maybe we learned, right? Like, I mean, I'm not sure.
Yeah, we did this in probability and linear algebra.
Okay, yes.
Yeah. So, okay, good. So let me give you a few moments to go back and think. We go and think, what is it that's going on here? If the WIs are, okay, by the way, I should write it a bit more statement. So if I have the YIs are the WNI, meaning the where Wn is the ith root of unity, where W or n plus 1, right? N plus 1 is the n plus 1th root of unity. Then this representation P of W0 to P of Wn, okay? So this is called the discrete Fourier representation. Discrete Fourier representation of a polynomial. You might have already understood it that it has relation to Fourier. This is a big important area where it goes into the area of harmonic analysis and all. If you guys, I mean, none of you are engineers, but if you have any knowledge from the engineering world, this is used a lot for the Fourier transforms and all those things that goes on for converting electrical signals from analog to digital and digital to analog and so on.
So Fourier transformations are trying to represent any function as a linear combination of some canonical basis. So here the canonical basis is this 1x x squared. And
right. I mean, Fourier representation not from a canonical basis, but some other basis. It's usually it's representing in a non-canonical basis, you can think of.
Okay, right.
Yeah. It's representing in a completely different basis, but which kind of helps us to understand it better.
Okay. So if we take inspiration from that, maybe the inverse will just be instead of e to the power.
Yeah. So I would now going to leave you, not leave you for, I mean, I will give you some time to think about that. If I am giving you the A0 till AN, and this is the coefficient thing, how do you produce this? Okay, maybe I will just, for the heck of it, let's call this one as y0 to yn. Okay, this I'm going to use this notation just for the, so where basically what I mean is that yi, let's put this one yi as p of wn plus 1 I. Okay, how do you move between these two things quickly? Okay. Of course, order n square algorithm is there, right? Order n square algorithm, you can move between a coefficient representation to any evaluation representation. But now we are talking about evaluation expression of a particular kind, right? You guys have discussed on various techniques, and all of the techniques will be useful. And I want you to think how to convert them. I can even give you some hint. So till now you have managed to get order n square algorithm for doing it using this extra condition. Okay, so this is also called the DFT, or discrete Fourier transform, and this is the coefficient one. You can move. So if I give you the coefficient representation, okay, you have to go to the DFT representation. Once you go to the DFT representation, multiplying here is very easy, right? So DFT for P and Q, you can DFT for P times Q. So this is an order n algorithm. This is nothing because this is the evaluation algorithm we just now saw. And once you multiply for P and Q, right? I want you to, so this is polynomial representation for P and Q. You move to this, you multiply, and then what do I want to do? I want you to go back to the coefficient representation for P times Q. Okay, so this is one direction. So maybe if I can take this one as the forward direction, this is the, and this is the backward direction, right? So till now we have seen, that this can be done in order n square. This can be done in order n. This takes order n square. So this basically means that the whole thing takes order n square, right?
Yes.
I want you guys to say that with this DFT representation, I want you to push it down lower. And I say that you can do it here and even the otherwise. So think about it. How you are going to push this one from the coefficient representation to the DFT representation. Not in order n squares time, but in much lower than that, order n log n.
So the log n is kind of inspiring a divide and conquer approach, right?
This should inspire a divide and conquer. Think about it.
Okay.
Yes. Okay. It's a polynomial. It is conflict. It is roots of unity. So you have to go a bit more deeper than just high level thing. But believe me, most of the techniques are there already. Okay. So yeah, let me give you 5 minutes to think about it.
So do we know anything of the form of the inverse of this VDM matrix?
Forget the form, forget this part. I would suggest that first think about this.
Okay.
This direction.
Okay.
So I can give you a hint. Think about this technique that you guys have kind of already pointed out. This technique. Something similar to this. Something similar. I'm not saying that it's exactly similar, but kind of in this direction.
So does it involve doing n separate log n
No,
steps? Like,
no.
so we can't be individually evaluating p of yi for every I, right? We have to do some sort of a.
Yes.
Okay.
You will do P of stay for every I, but that will not be log n times n. That no, not that direction.
Sir,
Yeah.
can we just go down to the matrix representation?
The matrix presentation. This one.
Where you multiplied the two matrix. Okay, yeah, this one.
Right.
Sir, if we divide the matrix in 4 parts, in half,
Right.
then okay, so look at the left, the upper left side matrix, and then the right side matrix.
Right.
If we take y0 to the power n by 2 common from the right side matrix,
then they are same, right?
right?
Good.
So
Very good. So this is
becomes Tn is equal to 2Tn by 2 plus n. That is order of n log n.
Very good. So that is a very nice way of solving this. Okay. But maybe I can, but there are multiple ways of doing it actually. So this is one technique of doing it.
So could you repeat the technique?
So, okay. So I will explain it in a different way. Okay. But why don't you guys think also once more? Okay. What's going on here? Okay. I mean, your friend has kind of pointed out a very important thing. I mean, even if you don't want to look at the matrix, that's fine. Okay. But the fact is that the matrix has a lot of structure in it. Or the set of yi's have a lot of structure in it. And that is exactly what you have to solve. Okay. I mean, your friend has solved it in one way. There is other ways of doing it also.
So doesn't that technique just use the fact that the yi's are in geometric progression?
Yeah, kind of. That is one important thing that you need.
But so we don't need e to the power I by n plus 1 times pi to be that geometric factor, right?
Not exactly, but yeah, why don't you solve it and then we'll see. I mean, yeah, small things will come up there.
Okay.
See, basically, idea is what? Once you have seen n log n, you have to do divide and conquer. Right? It's a recursive kind of stuff. It's a recursion that you have to do. That's clear. Right? Something like this merge sort kind of stuff, right? So you have been given two polynomials, p and q. Oh, sorry, forget p and q. You have been given a polynomial p, right? And you have to solve p at the w n plus 1 0 till w n plus 1 n plus 1, right? You have to solve it at all these points. So of course, one thing is that you have to split it up. What do we split? Do we split this part or do we split the polynomial? So let's think of the polynomial to be a0 plus a1 plus an x to the power n. How do we partition this polynomial into two polynomials such that evaluating P can be done by looking at the evaluation of the smaller polynomial.
So we can just split it in the midpoint, at the midpoint.
Will that help? That is one way of doing it.
Sir, we can take this x common, like
Okay. X of what common?
from A1 to like A. If we Google that, wait, sir.
Right. Okay.
So, but
So I was
itself
thinking,
is-
Okay, go ahead. So standard, so that multiple ways. One way is you can split up in the middle. The other way is to split up into two parts. Okay. Let's call this one Q1 and or Q0 and Q1. What is Q0? Q0 is A0 plus A2 x squared plus A4 x to the power 4 plus all the even ones. Q1 is nothing but A1 x plus A2 x cube plus all the odd ones. So if I just, in fact, if I take away x out from all of them, what do I get into x? So P of x is nothing but Q0 of x plus Q1 of x into x, right? But say, what is it that we want? We want the evaluation of P at all the points, right? At so in fact, what do I mean? Yeah. So if you think of this one, Q0, what is the Q0? Let's see. So Q0 is of course A0 plus A2 x squared plus something, right? So this is, if I write Q of x as, so maybe if I want to write it, if I use a different notation, maybe Q0 tilde as A0 plus A2x plus this one, which basically means that Q0 of x is nothing but Q0 tilde at x square.
Yes, sir.
Right? So I want to evaluate P at a power of unity, right? I want to solve P at W, say omega, for some omega, some power of unity. What is this one? This basically becomes Q0 tilde at what?
Omega square.
Omega square plus same way
X times Q1 tilde omega square.
Q1 tilde times omega square. Now, what is this one? How big is this? What is the, can you say about the coefficient of this? Sorry, the how many, what is the degree of Q0 tilde? What is the degree of Q0 tilde?
N by 2.
It is n
Like
by
that,
2.
like.
Similarly, the same as degree of Q1 tilde. Right? So in Q0 tilde, right? If I had to convert the coefficient representation to the discrete Fourier representation, I had to evaluate Q0 tilde on all the n by 2th roots of unity. right? But
Yes.
because the omega is the nth root of unity or n plus 1th root of unity, whatever, therefore q the omega square is the n by 1 by 2th root of unity. So if I have a algorithm that takes in any vector of size n and outputs where n can change with time, and outputs is DFT representation, then how can we use it? So maybe here I've just actually opened up this algorithm. See here, this is from the book of CLR, format search and request. Okay, so what they have done is that they have this A. Okay, so first of all they have this nth roots are this is the nth root of unity, right? Omega n, and they have this A, which is basically the set of coefficients that was there. So they are using this is n. So I mean, I was using n plus 1. They are using n. Okay, so a0 to n minus 1. They have split up into two parts. One is all the even ones, and the other one is all the odd ones. The idea is that you first use this algorithm as a recursive call to obtain the DFT or the discrete Fourier transform of A of 0, meaning of Q0 tilde, as we just now talked. You also use the CFT to obtain the DFT for A1. Okay, that means Q1 tilde. And once you have that, you can write down the coefficient of, I mean, all the values by doing the same thing. This is all that we are doing, right? So this is basically P of so P of W equals to P of omega equals to Q0 tilde of omega square plus omega times Q1 tilde of omega square. And since y0 is the DFT representation of the polynomial Q0 tilde, and y1 is the DFT representation of the polynomial Q1 tilde. So now I can just do a simple simple loop and just compute all the roots, and I mean all the evaluation of the original polynomial at all the roots of unity. Okay, so let me give you a couple of minutes to think about it. So in short, what is this recursive FFT giving? You are submitting a set of coefficients, okay, a polynomial of length n, the coefficient representation of that, so a vector of length n, and it is outputting another vector of length n, which is basically the evaluation of these polynomials as those nth roots of unity, as at the nth roots of unity.
So where we are using the fact that we've chosen this special structure for the yi's is the fact that in one iteration we're getting rid of two calculations, right?
Right.
Because this is we can determine yk as well as
you told you that. So there's two things that where I'm using the important structure. One is the geometric structure.
Right.
The other one is the fact that the omega square is a n by 2th root of unity. See, because when you are solving it here, right?
Right.
So recursive FFT for A0, what is it that I'm getting? I'm getting, so this is Q0 tilde, right?
Right.
Q0 tilde at the n by 2th root of unity.
Oh, okay. So that is why we can use it again in the recursion.
Right.
Okay.
Okay, so these are the only two properties of the roots of unity that we are using.
So, and it's also the fact that yk is equal to yk q0 tilde plus q0 tilde at omega squared plus omega times q1 tilde at omega squared, and another update is happening here, right? Which is
this one is
right.
actually not necessary. You can do that one. That helps you to solve it a little quicker. Okay, it is not something too important, but you can do that. And this, if you want to do this thing, then you need the fact is you need another property of the unity. That is kind of the reverse. This the 1 by omega is also a root of unity.
So, but then if we didn't add this iteration here, wouldn't this be a loop that we'll have to?
You have to go for n steps.
Right. So wouldn't that make it an order n squared algorithm?
No, it's not. See this. Okay. Now, what is the time complexity? So T of n. Okay. So this one is T of n, right?
Okay.
T of n times what is takes. All of these things are constant. This is order n, right? Whether it is k0 to n by 2 or k0 to n, this is an order n algorithm. That's it.
Okay. Right.
Right. So it is T of n equals to order n plus you have calling this one at n by 2. So T of n by 2 plus T of n by 2.
Okay.
Okay. So you have, yeah.
So hypothetically, if we were to try this for just a general geometric progression, where will we get stuck? Because let's say
exactly the most important place where you will get stuck is this one. But how will you ensure that? See, we are using kind of by default that the algorithm almost naturally without knowing anything, right? It is going to solve. It is going to compute q0 tilde at the n over 2th root of unity, right? And that will help us to solve p over nth root of unity. The fact that if w is a nth root of unity, then w square is a n by 2th root of unity. This part we are using. This is not guaranteed by any other set.
Because we want to write this equation as T of n equals to T of n by 2, and n by 2 features as it is the n by 2th root.
Yes. Because otherwise, I mean, we have, so see, this one is giving us one, this is going to give us one vector of size n by 2, right? This is also going to give us one vector of size n by 2. We have to combine these two to get a vector of size n by n. Right. Now, if this is a vector that computes it on some set of points, this computes it on some other set of points, how are we going to combine these two to obtain a set? I mean, even if it's a geometric thing, right? Then, I mean, then the geometric structure has to be dealt with carefully.
Okay, right. Yeah, it's a bit complicated, but yeah, I got.
Yeah. Yeah, so this is what is known as the first Fourier transform. That is why you have seen the names of FFT here. It's recursive first Fourier transform. All it does is converting a coefficient representation to the discrete Fourier representation, the discrete Fourier transform of that polynomial. Right. Now, if this is a vector that computes it on some set of points, how are we going to combine these two to obtain a set? I mean, even if it's a geometric thing, right? Then, I mean, then the geometric structure has to be dealt with carefully. Yeah. Yeah, so this is what is known as the first Fourier transform. That is why you have seen the names of FFT here. It's recursive first Fourier transform. All it does is converting a coefficient representation to the discrete Fourier representation, the discrete Fourier transform of that polynomial. So maybe I have somewhere here. Let me see if I have it in the picture that I just drew. There should be somewhere. Yeah, something like this. Yeah. See, if you have been given two polynomials, you first use this n by log n technique to obtain the DFT representation. Then you do a pointwise multiplication to obtain this representation. And then you do this interpolation to get n log n.
So P of W, we obtained as Q naught of W squared, Q naught tilde of W squared plus Q1 tilde of W squared. Now, in order to obtain P of W squared.
Yes, what will you do? P of W squared?
So will we repeat that whole computation?
No, you don't, because this is already there. What is P of W squared?
It's Q naught of W to the power 4 plus.
Exactly, P naught of W to the power 4, right?
Right. Plus W squared times
W squared times W to the power
Q1
4.
tilde.
But W
Right.
to the power 4 is already. So what is FFT returning? What is this first Fourier transform returning? Let's see, what is this first Fourier transform returning? It is not returning one value. It is returning a whole array or whole list. Right? So the returning, so when you are, so if this is the thing, okay, so this is recursive FFT, what is it doing? It is taking that A0, A2 till A whatever, n by 2 second or stuff like that, or n minus 1, right? Okay. So this is the kind of looking at Q0 tilde. And what is it outputting? It is outputting Q0 tilde at W squared, but W, I'm assuming W equals the nth root, okay? W squared, then it is doing it at all the other points, right? Q0 tilde,
Okay.
4, it's basically outputting this whole, it is outputting the evaluation of Q0 tilde at all the n by 2th roots of unity.
Okay, got it. Yes. So right. So in order to, so we're not even finding P of W alone. We're finding
Yes.
P of W squared, all of them together.
One, yeah.
And
so this is
that's
outputting one
okay.
vector.
Right. And its own subordinate will calculate for W squared, W to the power for everything.
Right.
And then we're just going to use that same, because all the powers of 2 are there in this.
Yes.
Right.
Okay. Okay, so this was something I would recommend you guys to go and read from. I mean, there are many books on this thing. This is one of the most powerful, or not simple and yet powerful techniques that is there in this called this first Fourier transform. And I would really request you guys to go and read from the CLRS book if you can, because that book has the best explanation for this particular section, I think. Okay. I am not going into the various other computational aspects of this FFT. There are the things about how can you design networks and how can you design something else for this first Fourier transform, and how is this connected to the whole concept of pattern recognition and machine learning, and how is it related to converting analog signals to digital signals and so on and so forth. It's a massive thing. Many of it is coming, I mean, maybe to understand or appreciate many of the applications, you might have to have a bit more understanding of some engineering fields, which possibly you are not yet familiar with. But in terms of this FFT, fast Fourier transform, this is basically what it happens. You just, instead of writing it as a coefficient, the first observation is that instead of writing it as a coefficient, set of coefficients, if we write it as a set of evaluations, if we write the polynomials as a set of evaluations, then multiplication becomes easy. Second option, move between the coefficient representations and the evaluation representations. That is in general very complicated. But if we choose the points to which we want to evaluate it, then if you can do it carefully, then that's outstandingly easy, or they can become very easy. Okay.
So the last step is still unclear, right? How do we talk about doing the inverse?
No, how do you learn the inverse? Okay, so actually, I have not done it here, but actually you can even write down the exact inverse very easily over here.
And it turns out to be a VDM matrix as well.
Yes, it's a very, it's, you can write it very, yeah. So I leave it to you guys to go and really work.
So is the VDM matrix, so the inverse of this VDM just replacing e to the power I by n plus 1 times pi by e to the power minus I n plus I by n plus 1 pi?
The inverse, you mean?
So in the van der Waals matrix,
Yes.
wherever we're finding a y1 or a power of y1,
right?
Can we just replace it by y1 inverse? And would that be the inverse VDM matrix?
No, it will not be the inverse.
Oh, it won't be. Okay. Because the Fourier transform, we've seen the
not
inverse
too far from that. Actually, you can see it here. This jkt of vn minus I is something. Yeah, you're kind of. Yeah.
Oh, okay. For okay.
Actually, it will be the inverse. Actually, you're right.
Yeah. Right, because in the inverse Fourier transform, we've seen that it has a very similar form.
Right. Yeah.
So motivated by that, we can even think about trying to prove something like this.
Yeah.
Okay.
Yeah. So I think I will stop today. I can go on for some more time to explaining about the Fourier, how Fourier analysis. So this is what you have just shown is Fourier transform. But one thing that comes up very naturally in the whole computer science world is what we call as the Fourier analysis of Boolean functions. Okay, particularly what we always want to understand in computer science is Boolean functions, functions that takes 0, 1 values. So not just generic functions, right? They're not so not functions whose range is real, but functions whose range, the domain can be real. So maybe I should just share it for a second. This is something that, of course, is not there as part of your course in some sense. So in general, when we talk about functions, we think of say r to the power n to r, right? Functions like this. But in computer science, what we are mostly interested in is something like r to the power n to 0 and 1. So functions that are polynomials that take such values. And in even more specifically, we can also look at functions of this form. So they take in, if you put in, so if you think of this function as a polynomial, a multivariate polynomial, then if you put zeros and ones in its coefficient, in its variables, then the output comes out to be 0 and 1. So if we are not doing this computation over F2 or something, everything is being done over the reals only, or the complexes. But what kind of functions are these? We want to study them. everything, starting from classification of this image classification to learning objects and all. It's all about this kind of functions. And a big part of how to approach this class of functions is using what is called as the Fourier analysis of Boolean functions.
So you said we're not doing these computations on F2, but then what if we have multiple coefficients which are 1?
Yes, so it can have multiple coefficients which is 1. So any function like this, not over F2, this is over R, okay, over reals. But any function of this kind can be written as a polynomial over R. Over R. Okay.
Okay.
You can write it as that. Okay, so this is called the Fourier spectrum or Fourier composition. And Fourier analysis of Boolean function. So this is way beyond the scope of this particular course. If you guys
So-
are interested, I'll be happy to talk about it
Is
independently.
it something like a K-map analysis? I mean, where we're trying to make an SOP kind of decomposition over 0,1 to the power n?
So okay, so you are really forcing me to go beyond what I wanted to do.
No, sir. This is just something we had learned a bit of in 11th and 12th. I mean, not even all of us. So maybe.
No.
Not K-map. You can explain what is K-map?
No, it doesn't need to be a K-map or something. So if I tell you a function, okay, how will you explain me the function? How will you tell me the function? So this function you will give me as, okay, so this function is so, and say let's talk about that, say multivariate, multilinear function, multilinear. Okay, so what I mean is that, say, say if this is a multilinear polynomial, meaning any coefficient, any monomial here is just product of some variables. Okay.
Okay.
So this can be written as summation of, you choose any subset of this set of variables, right? If A of S, product of xi, I is in S, right?
And AS is just any real number.
Okay, I messed up big time. Yes, I gave you the punchline already. So sorry, forget whatever I just told.
Okay.
Yeah, so forget that. Okay, so if I give you this function, okay, and so these functions takes the values, say 0 and 1 to the power n, and output some numbers, say real numbers.
Right.
Okay. How will you give me this function? Okay. You will give me by saying that, okay, see, at all 0 the function value is, say, y0. At this the function value is y1, and so on and so forth, right? The evaluation at the function at all the 2 to the power n points, right?
Right. Yes.
So this is the most standard way of writing a function or giving a function.
Right. This is the most primitive way in
This
a
is the
way,
most
right?
primitive way of presenting the function.
Right.
Okay. Why is basically in some sense okay. But now consider this function. Okay. So chi s of x, x1 to xn. What is chi s of x1 to xn? This is a very simple function. It is nothing but the product of those set of variables that are in S.
Okay. And we're not multiplying to this product the
Nothing. Just this much. Okay.
Okay.
Just
Okay.
consider this function. So this
Right.
is what is called a linear function. Okay. It's a linear function. It's just a multiple, one single monomial.
Okay.
Okay. So it so turns out that these linear functions, okay, so you can define a inner product space of all the functions
Okay.
from 0, 1 to the n to 0, 1. And you can prove that the set of linear functions forms the orthonormal basis in that.
Okay. Right.
So which basically means that any function can be written as a combination of linear functions. Which basically brings us to here. So any function f can be written as a set of linear functions.
Right. Okay.
Okay. So instead of explaining the function by giving you the evaluation at all the points, I can also give you this function by telling you the coefficients of those monomials.
So can't we say that okay, one direct way to extract a function form out of just that list would just be to say that okay, let's see for any given input. So let's say we look at a certain entry of that list where there was a set S which had all ones and the rest were all zeros, and
Right.
the function was evaluating to some AS for that, or so let's call it YS for that,
Right,
for
yes,
that
yeah.
entry. Then can we write
AS
this
is equals
as
AS equals YS? No.
no,
It's not.
AS is not YS, but Y we can write this as something like just a second. Yes, sir. We can write this as YS
Actually, I made a
times.
mistake over here. I was doing it here. You don't write it here. You do it. Okay, so this will be. You have to prove that these are the linear functions. So this also do come down to if you change the notations a little bit more, and if you think of these functions f as functions from plus minus 1 to the n to plus minus 1, then this can be written in the way I had written earlier.
Oh, okay, right. Yes, sir. Right, I agree. So because we can think of that as the other form as simply product of xi's in S times product of 1 minus xi's which are not in S times ys.
Right.
We can just sum that all up, and I
Right,
think
right.
we can reduce it to this form, right?
Yeah.
Oh.
So understanding Fourier or understanding Boolean functions or any function for that matter boils down to understanding this set of coefficients.
Okay, right.
So what are the properties of these coefficients? What can you learn those coefficients? Can you estimate those coefficients? How can you go about it? So there are many things, properties comes up. So this opens up a huge area of research, which is used both in pure mathematics to computations of all kinds, everything. So this is what is called Fourier and Boolean functions, and the basic idea is exactly the same thing as we just now did. Instead of understanding a function as a representation of not representation, as a evaluation of functions at some point, we can also look at it as some coefficients of some in another basis, right? And that's how we want to extract this whole stuff. Anyways, so if you guys have not understood whatever I just now told, just after this one, don't worry about it. So this is just was beyond. This was just for some kind of much high level stuff. But I hope that you guys have understood somewhat at least of the FFT algorithm, and I really ask you guys to go and read this FFT algorithm over here. It's a very nicely written algorithm. algorithm that has been there with all possible things done, all possible calculations computed and all. So, and you can see the beauty of both recursive algorithms as well as understanding the concept of the various algorithmic techniques that you have done so far. Okay, so before I stop today, any questions?
Sir, do we know if n log n is the best we can do to multiply two polynomials?
Yeah, you can prove that n log n is the best. You can prove. You can try it out yourself. Okay, it's not obvious, but you can do it.
Okay. So somehow we have to show that multiplication of two polynomials is at least as hard as FFT or something like that.
No, it will become that multiplication of two polynomials is as hard as sorting control.
Oh, okay. Or maybe we can even use a tree argument.
Tree argument here will not give you immediately, at least.
Okay.
Of course, everything goes back to the tree argument.
Right.
But seeing it directly from the tree argument is not easy.
Okay. And sir,
yeah.
In the last class we had a few homeworks, but at least I don't know if I didn't get a solution for them. So can we discuss that?
What was the homework? Oh, this Hopcroft card thing, right?
Right.
Yes. So maybe you can discuss it actually in the maybe it's in the tutorial section this week.
Okay. Okay.
Okay. So.
All right. So, and also that other question about finding a maximum matching for a general graph. We've seen it for a bipattern.
Right. But we had already this Hopcroft curve will give you a maximum. I mean, will give you algorithm for that also.
Yes.
Right.
So
yeah.
Weren't we looking for a network kind of approach?
Oh, okay. There is one. Can you use it to get a network thing? Yes. Can you reduce it to flows?
Right. Right.
Yes. Yeah. So that also was a question that was given.
Yes.
Yeah. So maybe I will ask the TS to have a discussion on that. I mean, all those things in the tutorial section.
Okay.
Okay, so I think another thing that I want to say is that there are 3 more weeks left. Okay, and please pass on this information to all your friends who are coming or not coming. That see, if there is a lot of things that I can do right now. Okay, there are certain topics and certain things that I kind of skipped beforehand. I can go back and try to solve and do them and all. Okay. So for example, finding convex hull of points and so on. There's a few topics there that I can cover. But also, I would prefer if you guys, instead of trying to cover too many stuffs, if you have some doubts on some problem, some areas, like, okay, I have not understood, say, dynamic programming part. Can you explain this thing or something like that? If you guys come back and at least let me know before the class a little bit, even if a few hours before that is good enough, then I would be happy to go back and discuss those topics. Okay. So I am basically kind of a division kind of stuff. I know this it's the end of this year. The new year is coming. You guys are also possibly parting mode and all. And also I don't want to really push through too many things. So that is not the goal of this whole course. I think the most important goal is that whether your foundations of the algorithmic understanding is solid. So maybe if I just press one second, just give me 1 second. I will just show you one quick. I was just going over the contents of the CLRS, and I can point out these things that I have done. and I plan to do, which are things I have not done. So please go and tell your friends that these are the things that basically has been done. And if they want, or if you guys want, you can just let me know any topic that you want me to repeat or revise. Just 1 second. Yeah. Let me share my screen once again. So if you guys can see, so in this, so these are like this most obvious kind of stuff that was there. We have done some of it, at least gone over some of these techniques in here. Okay, so these are the foundation. I'm looking at the CLRS book. Okay, the Corman book. You can look at any other book also. That's perfectly fine. So the thing that we have done, or we should have done, is the sorting problems. Okay, sorting this heap sort, quick sort, smart sort, sorting in linear time, median, and these things. We have not done data structures, okay, at all. We have done this subject, this dynamic programming. We have gone through greedy algorithm, if not all, but some of the problems that has been done over here. We have not done amortized analysis. Now, this is something that I might start if I have time. Okay, I have not done advanced data structures also. I have gone over graph algorithms. Okay, elementary graph algorithms is topological sort, breakfast sort, DFS, EFS, minimum spanning tree, all single short shortest path, all pair shortest path, and maximum flow, both forceful Curson and this maximum bipartite things. Okay, so these are basically what I have done. I have also done a little bit of this linear programming, not too much. I have just given you some ideas, a little bit, and I have done just now. I did Fourier transform, FFT. Okay. Now, other than that, yeah. So I have also done this part, the NP completeness part. Okay, the polynomial time, polynomial. So there are of course things that I have not done, as you can see. Like for example, I have not done much number theory algorithm techniques, except for this great GCD that I did a little bit. I have not done computational geometry, not a single thing. And approximation algorithms, I have just done a little bit, this vertex cover problem. That is two approximation stuff, right? I did. And yeah, so that's about it. So these are the topics. If you guys want to take a note of it, I will be happy to kind of repeat the thing that I talked about. So in the CLRS book, the sorting and searching part, dynamic programming, greedy algorithms, then in the graph algorithms, the basic graph algorithms, minimum spanning tree, single shortest path, all pair shortest path, max flow. And we did a little bit of linear programming, FFT, and NP completeness. These are the things that we have mostly covered. So if you guys want, I will be happy to go over any of the previous topics that you have done or we have covered, and I revise this whole thing. And else I will just go into another topic and try to cover some more stuff. Okay.
Okay, sir.
Yeah. So, okay, good. So, see you on Thursday.
Thank you, sir.
Thank you, sir.
Thank you. Thank you.
Thank you, sir.